In this video, we're going to be solving a Unit 8 fluids FRQ. So a large cylindrical tank filled with water is open to the atmosphere at the top and rests on the ground. The water level is maintained at a constant height h above the ground. A small hole is drilled in the side of the tank at a height y above the ground where 0 is less than y is less than h. The water exits the hole horizontally. Assume the fluid is incompressible and non-viscous, the tank is large, and the speed of the water surface is negligible. The pressure at both the water surface and the hole is atmospheric, and your gravitational acceleration is g. So this is our setup here, and y is measured from this point to this point. And first we're asked, from starting with Bernoulli's equation, derive an expression for the speed v of the water exiting the hole in terms of g, h, and y. So we want to get the exit speed, and we're going to use Bernoulli's between the 2 points. So we're going to make point 1 be the water surface, and let's make point 2 the hole. So let's define our variables. So P1 So now let's write our equation. Now we can cancel our common terms. You can also cancel your row. We can solve for v. So this is your answer for A. So we want to find the time of the flight. After exiting the hole, the water behaves like a projectile. Derive an expression for the time t it takes for the water to reach the ground in terms of y and g. And we know that's going to be a projectile. Therefore, Vx is going to be constant because acceleration is change in v over t, so that means you had to have 0 over t, which is making your ax equal to 0. Now, then in our vertical direction, you only have, wait, or negative g is equal to ay. So we're going to use vertical cake kinematics. We know Vy is initial because water exit horizontally. And we know that vertical displacement from the ground is going to be 0 minus y. So we're going to use this equation. Then we substitute in. Because again, we can track, we have g here for delta y. For Vy, we had that this was equal to 0. Now, if you multiply both sides by 1, so this is going to be your answer for part B. Now we're asked for C, what is the horizontal range? Derive the expression for the horizontal distance r from the base to the point that it hits the ground. So again, here your range is going to be this horizontal distance because of projectile motion. So we can use Newton's second law horizontally. So ax is equal to 0. We know that horizontal speed stays constant. At your exit speed. So we know our range formula from kinematics is equal to Vx times t. So we already have our expression for Vx. We know that for V, we have this. And for t, we have this expression down here. You can combine this under one radical. You can cancel out the g. You can take 4 out. So this is your answer for part C. Now for part D, we're asked what is the maximum range? Determine the value of y in terms of h, for which the horizontal range is the largest. So we're asking when or what y makes r the largest. So we already have this from earlier. So since the square root function increases when the inside increases, we have to maximize this. So this is the same thing as if you distribute. So what this equation is it's a downward open quadratic because you have a y. Or no, because we're just gonna say that that's the variable, right? We can choose that. We can treat it like an x, but it's gonna be downwards because you have that negative sign. So this is gonna be the max at your vertex for f of y. That means your vertex, using your formula, is y is equal to negative b over 2a. Here a is equal to negative 1 and b is equal to h. So we have y is equal to negative h over 2 times negative 1, which is h over 2. So you have your range is going to be the greatest when the hole is halfway up the water height. So y is equal to h over 2 is going to be your answer. Now, for part E, we're asked a comparison of two holes. Two holes are drilled in the tank, one at y equals h over 4, and one at y is equal to 3h over 4. Compare the horizontal ranges of the two streams, state whether one is greater than the other, and whether that they're equal, and justify your answer. So we're going to use our range formula for both of these comparisons. That's R1. So you're going to have R2. So we can see that R1 is actually equal to R2. And that's because we have a projectile motion, and projectile motion is symmetric. And this is for expression y equals h minus y about y is equal to h over 2. The two horizontal ranges are equal. Now for part F, we have a pressurized tank extension. So the tank is now sealed at the top, and the air above the water is compressed so that the absolute pressure at the bottom of the surface is PO, where PO is greater than P atmospheric. Starting from Bernoulli's equation, derive an expression for the new exit speed of the water in terms of PO, P atmospheric, density, gravity, height, and Y. And for 2, okay, we'll just do 1 first. Then you can multiply by 2. And V is equal to this root. Now let's look at our part 2. So state how the horizontal range changes compared with the original open tank case. Indicate whether it increases, decreases, or remains the same, and justify your answer. So we know that our hole is still at height h. At height, I mean y. So vertical motion stays same. And we know that t is still going to be 2y over g still. Therefore, only change is going to be your horizontal speed. And since we know that P initial is greater than P ATM, that means that this is positive. So exit speed is larger than before. because R is equal to VT and T is the same while V increases, that means that R overall will still increase. So we can say that pressurized air adds pressure energy, which is gonna increase exit speed while T flight is the same.